All right, so in this video, we're going to take a look at continue with the Pascal's triangle, but we're going to take a look at it and describe it in a different way, right? So we have this number that we're going to define here, where we write like this, right? Not a fraction, but it's the choose number. So it says n choose k. Right, or if we can think of n as being the total number of objects, and then we're going to choose k of them, right? So 5 objects, we want to choose 3 out of the 5, right? And how many different ways can we select these k objects out of the n total, right? So as it turns out, right, our Pascal's triangle represents just that, right? Again, if we think of, all right, we always start at 0, the first row, second row, third row, etc., right? Let's do the 4. Okay. All right. Now, what we can think of that lattice problem where we started at 0, 0, right, and let's say we wanted to go to the point 2, 1. Right, we can interpret this problem as a choose problem here, right? Where we added 2 and 1, so that was 3. And again, it didn't matter which one we chose, right? If we chose 1, right, really the way you interpret that is there are 3 ways that you can move up, right? And you only want to do it once, right? You want to choose one of them, right? You see, there's 3 opportunities here, 1, 2, 3, but you're going to choose only one of them, right? So you can choose this one here, right? Or this one here, right? Or this one here, right? There are 3 opportunities to choose one, right? And whichever one that you do decide to choose, right, you fill in the other, right? 1, 2. All right, and you can think of it in the other way as well, right? Where you have 3, choose 2. Right here, our capacity are different, is limited, right? So instead of choosing the vertical route, right, I can choose 1, 2 in this direction, right? Or I can choose 1, 2 in this direction. All right, and then I fill the other one up with this one here, right? Or, right, I can also choose just 2 up here, right? In which case here, I fill it up with there. All right, so you can see how those are just equivalent, right? And if, again, translating the Pascal's triangle to the choose numbers, right, this is what it would look like, right? N, the number of objects, is always going to be the top number there. So all of these would be 1, choose 0, 1, choose 1. Right, the next one here, we'd have 2, choose 0, 2, choose 1, 2, choose 2. 3, choose 0, 3, choose 1, all right, 3, choose 2, 3, choose 3. All right, and you can see here that these are, in fact, the same, right? 3, choose 1, 3, choose 3, both 3. Okay? All right, and so forth, right? Now, algebraically, right, this n choose k number, is the quantity n factorial over k factorial n minus k factorial, right? So, for example, for something like the one we just did, 3, choose 1, we would get 3 factorial over 1 factorial, and then 3 minus 1 factorial. Right, and we would get 3 times 2 factorial, 1 factorial, and then 3 minus 1 is 2 factorial. You can see we could simplify that, and 1 factorial is 1, so we get 3. Okay, so that's algebraically how you would you would simplify those values. Or you could just draw out the triangle, right, and have it handy there. All right, now let's take a look at 3 other problems here, and then we'll see how those, while they may seem completely unrelated, how they actually are very much so related, and how we can interpret them as this, using the Pascal's triangle to solve this n choose k number, right? So first, let's start off with bit string. So we'll introduce what a binary digit is. So a binary digit, right, a number that is 0 or 1. I usually think of, right, on or off, right, 0 being off, 1 being on, or true false, right, when we're doing our truth table, 0 being false, 1 being true. Right, so those are the binary digits, and a bit string is a string of binary digits. Of binary digits. Okay, so any string, whether it's like this, like this, like this, like this, or like this. All right, so all those, each one of these represents a bit string. Right, now the length of the string is the number of digits, and the weight is the number of ones. All right, so an n-bit string is the bit string of length n, right? It's bit string of length L. Excuse me, length n. All right, and we'll use this notation here, where this is the bit string and then k is the weight. So here, B42, so it's all bit strings that are of length 4 and weight 2. So for example, 0, or let's list all of them out, right? And so 101, and then 0101. Okay, so there are 6, right? Actually, I know that there are 6 of them, right? And I'll explain why I know this in a second. Now, this might seem like we're really far away from this idea of a Pascal's triangle, right? But if we think of here the 4 positions here, right? And what we're really asking for is, out of these 4 positions, I want to choose 2 of them to fill with 1s, right? The rest get filled in with 0s, right? I'm centering, I'm focusing this on the weight being the 1s, right? So really what I'm asking for is, out of these 4, right, how can I choose 2 of them to have 1s, right? So I can choose them like I did here, right? And then I fill in the rest with 0. Right, I can choose them to be on the bookends here, right, or here, right? So I could do that, right? So what does it come down to? It comes down to, well, if there's 4 slots, how can I choose 2 of them, right? So I can look at my triangle and go to the 4th column. Remember, we start at 0, 0, 1, 2, 3, 4. And then we go to the second one. Again, always start at 0, 0, 1, 2. And we see that 6 right there. Okay, so now we could see that there are 6, or algebraically, All right, and this is 4 times 3 times 2 factorial over 2 factorial 2 factorial. All right, and then that simplifies to 1, so we get 12 over 2, which is 6. Again, confirmed. All right. Okay, so we could see here while we were talking about it seemed like something completely different, right? We're actually still talking about this choose number here, all right? Okay, so now how about a different problem here? Let's say we had a set A consisting of 1, 2, 3, 4, 5. All right, and I want to talk about subsets of A, right, that have exactly 3 elements. B has exactly 3 elements. All right, so I want to ask myself, how many different subsets do I have? Well, I can try and just enumerate all of them, right? I can say 1, 2, 3, right? Or 1, 2, 4, right? 1, 3, 4, 2, 3, 4, 1, 2, 5, 1, 3, 5, 2, 3, 5, 1, 4, 5, 2, 4, 5, and then 3, 4, 5, and then 1, 2, 3. Sorry, did 1, 1, 4, 5, 2, 4, 5, 3, 4, 5. I think and let's see, what else am I missing here? I think that's all of them here. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 10. Yes. So there are 10 of them, right? And again, I can confirm this, right? So there are 10 of these. I listed them all out, but I mean, again, right? Can kind of struggle to be like, oh, did I get all of them? How many are there? Well, again, right? Why don't we think of this in a different way? So we have the 5 elements, right? Being the numbers 1 through 5, the integers 1 through 5. And I want to think of this as, well, how can I choose 3 of them? All right, I can choose them like this, right? Or I can choose to do this, right? 1, 4, 5, right? So given 5 objects, right? The objects here being the numbers 1 through 5, I want to choose 3 of them, right? And how many different ways can I do that? Again, I can look at my triangles, right? 0, 1, 2, 3, 4, 5, 0, 1, 2, 3. You see 10. All right. Or we can again do the long way. So 5 times 4 times 3 factorial over 3 factorial 2 factorial. Let's see, that goes away. And we get 20 over 2 factorial is just 2. And we get the value 10. Okay, so now we could see here, right, how problems that we initially didn't seem related at all actually do have a lot in common in how we find them, how we interpret them, and just kind of the strength of this Pascal's triangle, how much structure is in it, from something that is very just kind of simply defined. Okay, now to wrap this section up here, right, another problem here that we can think of here is, let's say we have a pizza shop. Sells pizza. With an option of 8 different toppings. How many pizzas with 4 toppings can you make? All right. So again, I could list out the toppings and try to create 4 different pizza toppings, but we can think about it in a different way. All right. So we can think of, okay, well, what if I had 1, 2, 3, 4, 5, 6, 7, 8? Right? We have 8 different toppings, right? And I want a way to choose 4 of them, right? So again, we can think of it, we can relate it back to that set problem or the bit string, right? Where if we can think of the weight, right? How many ones there are being the number of toppings you want, right? So I can think of, all right, 1, 1, 1, 1. And all right, the rest get filled in with our zeros. All right, so we can, again, interpret it in a different manner, right? Where we can think of this as B 8-bit string with a weight of 4. All right, well, I know how to solve those now, right? Now that's 8, choose 4. All right, and we could say here, all right, 8 factorial, 4 factorial, 8 minus 4 factorial. And we get 8 times 7 times 6 times 5 times 4 factorial over 4 factorial, 4 factorial. And here, that reduces here. And we get here, and some calculating here. 4 factorial is 20. 4 times 5, 4 times 3 is 12, times 2 is 24. 8 times 7 times 6 times 5 divided by 4, 70. All right, so we have 70 different 4-topping pizzas that we can make, right? And as you can see, right, the bigger these numbers get, there are more different combinations to account for. So it just is more efficient to come up with a calculation that we can do, right? As opposed to enumerating all of these here. All right, now just kind of to wrap this up here, one thing to notice here, right? If you notice in our Pascal's triangle, it starts with 1 and it ends with 1 every single row. Now in terms of the n choose k number, that means that n, whatever row you are, if you're choosing 0 of the objects, there's one way to do that. And also n choose n is 1 as well, right? There's one way to choose all of them, right? If you think of it in terms of the pizza example, right? Well, what if you had one with no toppings, right? Well, there's only one way you can do that, right? A plain pizza, plain cheese pizza. And let's say you did all 8 of them, right? Well, there's only one way to do that, right? Just have all 8 toppings on there, right? So just keep that in mind here in terms of the choose number, right? The ends are 1, so what does that mean? There's one way to choose 0 objects and one way to choose all of them.